Alright, so I know what you're thinking. We've got this area under the curve we're talking about. How does that relate to anything we just did? And what was that business about antiderivatives? What's going on there? Alright, so our goal with this set of notes is we're going to try to go ahead and establish a link between these, the area that we're talking about, and this thing called definite integrals by using something called the fundamental theorem of calculus. It's got fun right there in the name, so you know it's got to be a good time. So recall that when we're trying to compute the exact area under a continuous function over some interval, we're taking the limit of the areas of n rectangles as n goes to infinity. So we've said that if we want to find the exact area, this is going to be the limit as n approaches infinity of delta x times f of x1 plus f of x2 plus f of x3 plus all the way summed up to f of xn, where all these x1s through xn's, these are our different points we decided to use. Maybe we used the left endpoints, right endpoints, midpoints, doesn't matter. Whichever one it is, that's what these are defining. And so this is the same as the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of xi. So this is the limit of the sums here. So how does that relate to this thing called the definite integral? Well, the definite integral from a to b is going to be the integral from a to b. This symbol here is our integral symbol. And it's the integral from a to b of f of x dx, which is the same as this limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of xi. So this is the exact area under the function f of x from a to b, or rather over the interval a to b. So here what we're doing is we've got these limits of integration. We have this thing here called the integrand. It's the function we are integrating, and our procedure is called integration, and we have this dx here called the differential of x. And essentially what this is doing here, this dx, this is something that's more important when we get into our higher levels of calculus where we use multiple variables. This lets you know what it is the variable is when you're doing this whole integration process. So remember before when we talked about implicit differentiation, how we had to have like dx's and dy's. Here the dx serves as a reminder of this is the variable we're talking about. That's all the more I'm going to say on it for now. If you ever get into a more complicated class, it'll come up a little bit more often there. Alright, so the definite integral is a number that does not depend on x. We could have used any letter in place of x if we wanted to. Like I just said, we're really looking at it being a bit of a placeholder. So the integral from a to b of f of x dx is the exact same as the integral from a to b of f of t dt, which is the exact same as the integral from a to b of, say, f of theta d theta. In all cases, these theta, t, x, we could use different letters if we wanted to as well, are placeholders for the thing we're integrating with respect to. It's a placeholder. It's a dummy variable. It just tells us which variable we're using, if it's x or t or theta. So let's say we want to consider a function greater than or equal to 0. Then the Riemann sum, so to be clear, this all these different integrals, and we take the summation of them, this is what's known as a Riemann sum. and this is our estimate. As we take the limit as n goes to infinity, and we get closer and closer to having an infinite number of rectangles, that's how we get what is known as the definite integral. Which gives us our exact area. Now, if the function's just greater than or equal to 0, this is really easy, right? We're just adding up all these rectangles, we're just finding this area, and everything's fine. So here, if we have a function that goes above and below the x-axis, so we've got some positive and negative and positive values, say this is some area 1, this is some area 2, and this is some area 3, then the integral from a to b of this function here, f of x dx, will be whatever we find the net area to be. So this will be a1 plus a3, since those are both of the positive areas, minus a2, since that's our area below the x-axis. All right, so before we get into kind of the exact formal definition of how we can use this notation in a useful way, let's see if we can use this idea to kind of figure out what the area or the integral should be. So say we wanted to go ahead and take the integral from 0 to 1 of the square root of 1 minus x squared dx. Well, this is the same as the area under the square root of 1 minus x squared from 0 to 1. And something that is worth noting about this is if we have y equals the square root of 1 minus x squared, this is the same as saying y squared equals 1 minus x squared, which is the exact same as saying that x squared plus y squared equals 1. So this actually means that we're looking at a circle centered at the origin with radius 1. So notice that the total area of the circle would be equal to pi r squared, which would be pi times 1 squared, which would just be pi. So that means that for us, we're looking at the integral from 0 to 1 of the square root of 1 minus x squared dx. We're really only looking at a quarter of the circle. So it stands to reason this would be a quarter of the area. So this would just be pi over 4. What if we had instead the integral from 0 to 3 of 1 minus x dx? Well, this is just y equals x minus 1. So it's a line with slope 1 and y-intercept equal to negative 1. So if we wanted to plot that line, we'd have here, 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 and here is our points. Play a little bit of connect the dots to get our line. But we're really is just interested in 0 to 3. So we'd be looking at some sort of area under the curve here. And this would be a negative area, right? It's below the x-axis, so this is a1. And then we'd also be looking at some area under the curve above the x-axis. And so this would be our a2. And so what you might notice about both of these is that they're triangles. And that's exciting because we know how to find the area of a triangle. The area of a triangle is 1/2 base times height. So that means we just need to figure out how wide each triangle is and how tall it is, and then we can figure it out. So for A1, this will be 1/2 times, looks like it has a height of 1 and a width of 1. So 1/2 times 1 times 1 will just be 1/2. For the other area, this will be 1/2 times, this has a width of 2 and a height of 2. So 1/2 times 2, which will be 2. So then to find the integral from 0 to 3 of x minus 1 dx, that'll be a2 minus a1, or just 2 minus 1/2, which will be 3/2, or 1.5. Either way is perfectly acceptable. Okay, so we can't go ahead, well, we could. We can't go ahead and find each of these little individual areas each time, or be expected to remember that this is the formula for a circle and figure that out at the drop of a hat. That's not exactly something that's realistic. So let's look at a couple of properties for the definite integral before we get into how exactly we're going to be able to use it in a very intuitive way. So far we've just been assuming that, so first things first, if we're talking about any functions f and g here, they're going to have to be continuous functions, right? That means that between a and b, we need to make sure we don't have any issues with continuity. And we just talked a little bit about continuity earlier in the semester. So far we've been assuming that the a is smaller than b. However, if we used had where our left endpoint, or our a was bigger than our b, then if we look at the integral from a to b of f of x dx, this is going to be the same as the negative of the integral from b to a of f of x dx. So if you ever need to change the order of a and b for whatever reason on your integral, that's fine, but it's going to be the negative of whatever that area was. Suppose for a second that a and b are the same thing, then the integral from a to a of a function equals 0, right? If you have a rectangle but the width of the rectangle is 0, you're not going to get anywhere. So that will have a width of 0. Say we want to take the integral of some constant function c. So this would be y equals c, or f of x equals c. Then essentially what we're doing here is we have some sort of constant function f of x equals c, and if we're looking at a and b being our endpoints, and we want to just find this area, well here, this is just a rectangle. So remember, the formula for the area of a rectangle is base times height, and the height is very clearly going to be c. And the base will just be whatever b minus a is. So this will be c times b minus a. Now let's say we have the integral of a constant times some function. Well, integral from a to b of c times f of x dx, this will be the same as if we pull c out to the front and then integrate from a to b f of x dx. If we have two different functions who we want to take the integral of, then what we'll do is this can be the same as the integral from a to b of f of x dx, plus or minus, depending on what you're doing, the integral from a to b of g of x dx. And if we ever want to go ahead and look at some sort of thing where we have adjacent intervals, say that we're looking from a to b on some function, but it really makes sense to go and kind of stop at some point in the middle and use a different way of finding the area for a second part. So say there's some sort of point C here, and between these two is some area A1, and between these two is some area A2. Well, then what we can do then is we can say that this is the same as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now notice where the c is here. It's a little bit of an odd place, but essentially you're going from here to here first, and then from here to here for the next part. And notice we kind of already did this when we tried to figure out those parts where we had the area above and the area below. Alright, so let's say that we wanted to use the properties of the integral to evaluate the integral from 0 to 1 of 4 plus 3x squared dx. Well, using our properties, this is the same as the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. So here, 4 is a constant. So this is a constant function. So the first integral will just be 4 times 1 minus 0. Now we still need to add this other integral. Now 3 is a constant, so we can pull it out. So 3 times the integral from 0 to 1 of x squared dx. Well, how do we find the integral from 0 to 1 of x squared dx? Well, it turns out this was the thing we were looking at last section, where we were trying to look between 0 and 1 and find the area under the curve of x squared. And we said from last section, the integral from 0 to 1 of x squared dx is equal to 1/3. So that means that at the end of the day, we have 4 plus 3 times 1/3, or 4 plus 1, which would be 5. Alright, now let's say that we know that the integral from 0 to 10 of f of x dx is 17, and the integral from 0 to 8 of f of x dx is 12, and we want to find the integral from 8 to 10 of f of x dx. Well, what we know is that the integral from 0 to 10 of f of x dx is going to be the same as the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx. And so what that means then is that we've got 17 equals 12 plus this integral we don't know, 8 to 10 of f of x dx. And so that then, of course, will tell us that the integral from 8 to 10 of f of x dx will equal 5. So essentially, we just had something where we knew that the area from 0 to 8 was going to be 12, and we needed to find out this other piece here, and we found out at the end of the day that the area under the curve there was 5. Now we have a couple of ways we can compare our integrals. If f of x is greater than 0, then if we have some interval a to b greater than 0, then the integral from a to b of f of x dx should also be greater than 0, right? If we're above the x-axis, we should have a positive area. If we've got some function that is greater than or equal to some other function, then the integral from a to b of f of x dx will be greater than or equal to the integral from a to b of g of x dx. If we have a bigger function, we get a bigger area. And last but not least, if we have some little m and big M that f of x is between, then since these are constant functions, this kind of goes into looking at this rule as well, then the m times the length of the interval b minus a will be less than or equal to the integral from a to b of f of x dx, but that'll be less than or equal to big M times b minus a. So again, to think about it, this is just the integral from a to b of little m dx, and this is the integral from a to b of big M dx. Alright, so suppose we've got this function here, and we're looking at g of x being the integral from 0 to x of f of t dt. We want to find the values of g of 0, g of 1, and g of 2. So notice here, we're saying that we've got a function that is defined as being the integral of some other function over the integral. So this here will be our f of t. If we want to look at g of 0, this is then saying that we have the integral from 0 to 0 of f of t dt. Now we talked about if you're going from one point to another, this should just be an area of 0 under the curve. Next will be us trying to find g of 1, which is the integral from 0 to 1 of f of t dt. And if we look at f of t here, if we go from 0 to 1, this first area here is just a triangle. So this will be equal to 1/2 times the base times the height, which will be base is 1, height is 2, and we'll end up getting 1 when we multiply all those together. If we want to find g of 2, this is the integral from 0 to 2 of f of t dt. This is a little bit more difficult for us to find, since here we would want to go ahead and figure out the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. And why is it that we want to do that? Well, essentially, these are different heights and different ways we would go ahead and find these areas. So this would be some area 1, and from 1 to 2, we'd have some second area, area 2. So we just found this first one, right? This is 1. And if we want to find the second area, it's a rectangle. So it's got a height of 2 and a width of 1. So 1 plus 2 times 1, which will give us 3. And we could keep going on. Say we wanted to use this to figure out what the third area was. We'd maybe make some different modifications on how we would go ahead and adjust that. All right, so what does all this have to do with calculus, right? We found a lot of areas, but why is that a thing that we care about? So this leads us to the fundamental theorem of calculus. It's got fun right there in the name. You have to be excited. It's how it works. I don't make the rules. The fundamental theorem of calculus is named such because it establishes a connection between our two big branches of calculus, differential calculus and integral calculus. So it's got two parts. The first part here is going to be a big blockbuster for us. So note that integration, or integral, is, and this is kind of the big takeaway, is anti-differential. In other words, it's going to be us doing the antiderivative. And that's what the fundamental theorem of calculus part 1 kind of highlights for us. If a function f is continuous on a to b, then the function g, defined by g of x equals the integral from a to x of f of t dt, where x has to be somewhere between a and b, is going to be continuous and differentiable on a to b, and the derivative of g equals f. So the derivative of the integral of a function is the function itself. So we could write this as d dx integral a to x f of t dt equals f of x. So what does that mean all at the end? Well, it means that if we take the derivative if we take the antiderivative of this, that's going to help us a lot with our integration. So how does that work with the bounds then? Okay, so we'll get to that. We will be getting there. But first, say we wanted to find the derivative of this function g of x. Well, the derivative of this function, 0 to x, square root of 1 plus t squared dt, by the fundamental theorem of calculus, we're really just saying we have to plug in x for t. So we've got the square root of 1 plus x squared as the derivative. If we wanted to find d dx of 1x of the integral from 1 to x to the fourth of secant t dt, then the problem is that the fundamental theorem of calculus only applies if x is the top limit. So we want g of x equals the integral from 1 to x of secant of t dt. Then what we'd be doing here is we'd be plugging in x to the fourth into g. So in other words, we'll get g of x to the fourth equals the integral 1x to the fourth secant of t dt. And chain rule tells us that we'd want to use our insides and outside functions. So the outside function is g of x, which is the integral from 1 to x of secant of t dt, and the inside function is x to the fourth. So the derivative of the outside is going to just be secant of x, and this is of course from the fundamental theorem of calculus, FTC, and the derivative of the inside is 4x cubed. So overall that means that the derivative that we're looking for is going to be secant of x to the fourth times 4x cubed. So this is where the fundamental theorem of calculus comes into play, part 2, and this is going to be an easier way to compute the exact area. So instead of us doing all these Riemann sums and trying to take the limit as n goes to infinity, if f is continuous on some interval a to b, then the integral from a to b of f of x dx is going to be whatever the antiderivative is, evaluated from a to b, and this is the way we'll notate that, and that'll just be the function, the antiderivative with b plugged in minus the antiderivative with a plugged in. So here, where big F is the antiderivative of F. So say we wanted to go ahead and find that area we loved from under the parabola y equals x squared from 0 to 1. Well, what that means is that we'll take the integral from 0 to 1 of x squared dx, and so we take the antiderivative of x squared. And so that means we'll take x cubed over 3 plus c. Since we don't know what the constant might be, it's going to be the most general form of the antiderivative from 0 to 1. And that means we'll take 1 cubed over 3 plus c, minus 0 cubed over 3 plus c. So notice that this here, this is the big F of x, this is f of 1, and this is f of 0. And so that'll be equal to 1/3 plus c minus 0 minus c. The c's will cancel and we'll just be left with 1/3, which is what we found on our own. Now notice that whenever we do this, these c's should cancel. So when we're taking these definite integrals here, where we're given bounds, we can just ignore them, because they'll cancel out. So let's say we want to evaluate the integral from -2 to 1 of x cubed dx. -2 to 1 x cubed dx. If we take the antiderivative, that'll be x to the 4th over 4, evaluated from -2 to 1, which means we'll want 1 to the 4th over 4 minus -2 to the 4th over 4. -2 to the 4th is 16, so we'll have 1/4 minus 16/4, which will give us -15 over 4, or -3.75. Either way is fine to write it. Okay, so now we have a much easier way of trying to find these areas under the curve. And so here, when we're going from -2 to 1, and the function is x cubed, we're going to end up having more negative area, or area under the x-axis. This is why we end up with a negative value overall. All right, let's do a few more. Let's say we wanted to find the area under the curve of cosine from 0 to pi over 2. Well, then this is just the integral from 0 to pi over 2 of cosine of x dx. And so this, the antiderivative of cosine, remember, is sine of x, and we're evaluating it from 0 to pi over 3. So this will be sine of pi over 2 minus sine of 0, which is the same as 1 minus 0, which is 1. So we can even do this to find the area under the curves of sines and cosines, which is great. Alright, so what if we wanted to go ahead and take this antiderivative? So we've got the integral from -1 to 3 of 1 over x squared dx, which, based on our rules, would be -1 to 3 x to the -2 dx. That would be x to the -1 over -1 from -1 to 3, or just -1 over x evaluated from -1 to 3. It'll be -1/3 minus -1 over 1, which would be, wait a minute, just want to make sure I did that right. So we've got -1 over 3 minus -1 over -1. That was it. That's where I made the mistake. So negative, 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 negative become positive, and minus, so it'll be minus. So we'll get -4/3. However, what you might notice is that 1 over x squared is always greater than 0, so this area shouldn't be negative. However, one of the things that we had said at the very beginning was that in order for us to do this, the thing we were integrating needed to be continuous on the interval. So 1 over x squared is not continuous at x equals 0, and 0 is on the interval -1 to 3. And so what does that mean at the end? It means we can't use the fundamental theorem of calculus. So what was the takeaway? The takeaway was that as long as we have a function that is continuous over the interval in which we wish to integrate, we can just go ahead and take its antiderivative and then plug in our upper and lower bound and do a little bit of math in order to figure out what the area under the curve would be, which is way easier than trying to find all these different rectangles. The rectangles are still good practice, though, so you will have a little bit of stuff where you're asked to do that. But going forward, we're definitely going to be using these antiderivatives to find our area under the curve.